All right, section 8.1. Testing the differences between means of large independent samples. And what that means is we're going to be looking at two different populations that are independent of each other. So last chapter we studied methods for testing a claim about the value of a population parameter. We looked at population proportions, population means. In this chapter, we're going to learn how to test a claim comparing parameters from two populations. So two samples are independent if the sample selected from one population is not related to the sample selected from the second population. Two samples are dependent if each member of one sample corresponds to a member of the other sample. So, and we've done independent, quite a few times in the past. I think you have a pretty good idea of what that is when you look at something. So, I'm not too concerned about that. But dependent samples are also called paired samples or matched samples. When we've used independent before. We're dealing with probability events. So, do you guys remember, like, dependent or paired is the example I use a lot of times is, does caffeine have a impact on your heart rate, right? So we take your heart rate and then give you a couple cups of coffee and then take your heart rate again, right? So the heart rate before, heart rate after, we would call that a paired sample. It's connected through one person, right? So that's the idea of what a dependent is. What we're talking about in this section is independent. Example 1, independent and dependent samples. Classify each pair of samples as either independent or dependent and justify your answer. Sample 1, resting heart rate of 35 individuals before drinking coffee. Sample 2, resting heart rate of the same 35 individuals after drinking 2 cups of coffee. Independent or dependent? Dependent. We just got done talking about that, right? The samples are dependent. Each sample is taken from the same individual. The samples can be paired to that individual. Sample 1, heights of 27 adult females. Sample 2, heights of 27 adult males. Independent or dependent? Independent. Samples are independent. The heights of the females are not related to the heights of males. Example 3. You guys try this on your own. Sample 1, test scores of 35 statistics students. Sample 2, test scores of 24 physics students who do not study statistics. All right, samples are independent. The test scores are from 2 different sets of students. All right. In this section, you'll learn how to test a claim comparing the means of 2 different populations using independent samples. It's important to remember that when you perform a 2-sample hypothesis test using independent samples, you're testing a claim concerning the differences between the parameters in 2 populations, not the values of the parameters themselves. Okay, so we're going to be taking the difference between the 2 samples. That's what we're looking at. We're testing the difference between the 2 populations. You can begin by assuming that there is no difference in the mean times of the 2 populations. So that'll be your initial assumption, that there is no difference in the mean times of, or I should say the means. Let's get rid of that. Means of the 2 populations. Okay. All right. For a 2-sample hypothesis test with independent samples, 1, the null hypothesis is a statistical hypothesis that usually states there is no difference between the parameters of 2 populations. The null hypotheses always contain the equal symbol. Okay, so there's always going to be a statement of inequality, and quite honestly, in this one, and for us, the vast majority of the time for this chapter, this type of test, we're going to be using equals, okay, and not equals quite a bit. All right, that's not all the time, but the majority of the time. The alternative hypothesis is a statistical test that is true when the null is false. The alternative hypothesis contains these symbols, right? Does not equal, less than, or greater than. And you guys are familiar with that. It's no different than what we've done with other tests, right? Oops. All right. To write a null and alternative hypothesis for a two-sample hypothesis test with independent samples, translate the claim made about the population parameters from a verbal statement to a mathematical statement. Then write its complementary statement. This is nothing new as well. You guys are familiar with doing this already. So here's the deal. The possible pairs that you can have for this type of test look like this. Okay, the mean from one population is equal to the mean of the other population. That's your first choice, right? That they're equal. Or you could have the null is that one is less than or equal to the other. And then the other option is that the null or the mean is greater than of population 1 is greater than or equal to the mean of population 2. Okay. So again, you're comparing the parameters from two different populations. You got population 1, population 2. Population 1, population 2. Okay, moving on. All right, a two-sample z-test for the difference between means. That's what they call this, a two-sample z-test for the difference between means. In the remainder of this section, you'll learn how to perform a z-test for the difference between two population means. 3 conditions are necessary to perform this test. 1, samples must be randomly selected. 2, samples must be independent. And then 3, each sample size must be at least 30, or if not, each population must have a normal distribution with a known standard deviation. Okay? So if the sample size is, if it's under 30, then we need to know this population is normally distributed with its standard deviation. Otherwise, it has to be greater than or equal to 30. Okay? If these requirements are met, then the sampling distribution is a normal distribution with the mean and standard error as follows. Okay? So what this is saying is this, and ultimately, this is saying the mean of the sampling distribution. If you guys remember what I talk about when I'm talking about with sampling distribution, right? If I have a population and I take a sample of 30 out of it and I find its mean and I plot it, and then I do that again. I take a sample of 30, I find its mean and I plot it. Take another sample of 30, find its mean and plot it, and I keep doing that. I create what's called a sampling distribution, right? And our hope is that sampling distribution would be a normal curve, kind of like that, right? Well, this is saying that the mean of that normal curve right here is equal to whatever the population mean for the first population is minus the population mean of the second population, right? And that would be right here. Okay? And then the standard error, or what is the standard deviation of that sampling mean, is given by taking this equation down here, right? It's the square root of the standard deviation of population 1 squared divided by the sample size from population 1 plus standard deviation of population 2 squared divided by n2. In other words, what this is this is the variance from population 1 divided by the sample size of population 1 plus the variance of population 2 divided by n2. Okay, and then you take the square root. So this sampling distribution would have this mean, this is all notation, and then it would have a standard deviation or standard error. It would be somewhere out here, right? These are the inflection points. And it would be okay. And hopefully it'll get a little clearer when we go ahead and try an example, okay? All right, so those are the equations you're going to use. A two-sample z-test can be used to test the difference between two population means when a large sample, at least 30, is randomly selected from each population, and the samples are independent, right? So sample size, at least 30, and samples are independent. Your test statistic in this case is the sample mean from population 1 minus the sample mean from population 2. Okay? That is your test statistic. Your standardized test statistic is z equals the test statistic, which is x bar 1 minus x bar 2, minus mu1 minus mu2. This comes, you see how I kind of put a bracket in blue above it? It's always 0. And the reason for that is this comes from our null hypothesis. And our null hypothesis for the vast majority of the time is going to be that mu1 is equal to mu2. We already kind of showed that, right? Well, if mu1 is equal to mu2, if you just do a little math and we subtracted mu2 from each side, do a little algebra, we get mu1 equals, I'm sorry, not equals, minus mu2 is equal to 0, right? Just by subtracting the population mean from the second population. So since this is equal to 2, that's what we plug in when we see mu1 minus mu2. It's always going to be 0. Okay? Now, when the samples are large, you can use S1 and S2 in place of the population standard deviations for both populations. Remember that? We've talked about that in the past, right? Our sample standard deviation S1 and sample standard deviation S2 can be used in place of the population standard deviations if the samples are large, meaning greater than or equal to 30. If the samples are not large, you can still use a two-sample z-test provided the populations are normally distributed and the population standard deviations are known, okay? So we have to be kind of aware of this situation. We can use S1 and S2 as long as the sample sizes are large, and if the sample sizes aren't large, we need to make sure that our populations are normally distributed and we know what their standard deviations are. Okay, guidelines. State the null, state the claim mathematically, identify the null and alternative hypotheses, right? So in our case, many times it's going to be this. Now, another way, oops, this is 1, sorry, 1, not 2, not equal to 2. Now, another way to write this same thing, because you'll see it both ways, is that mu1 minus mu2 is equal to 0. Right? That's what happens when they're equal to each other. The difference is 0. And is not equal to 0. So they are one and the same thing, and that's what we'll use quite a bit. Specify the level of significance. You guys are familiar with that. Level of significance, typically 0.05. We do use other ones. But the level of significance is equal to, or what that is the probability of making a type 1 error. We use that to find our critical values. You should remember that. Sketch the sampling distribution, right tail, left tail, or two-tailed. Determine the critical values, right? In this case, critical values are going to be Z naught. That's what we're going to find. If it's a two-tailed test, we're going to have a curve that looks like this. Our shaded regions are going to be on the left and the right. And each tail will have alpha divided by 2 area. Okay. And, you know, we would find a negative Z naught and a positive Z naught, if you recall. Okay. Determine the rejection region. So that's going to be these critical values. It's either going to be below one or above the other. And then we find a standardized test statistic. And I already gave you that equation. It's the same one. Remember that this part is typically 0. And then we're going to make a decision to reject or fail to reject the null hypothesis. And then we're going to interpret the decision in the context of the original claim. We've done that over and over again. If you need a refresher, there's that table on page 372. But by now, I'm hoping you guys have figured out that if the null is the claim, then we say either there's enough evidence to reject the claim or there is not enough evidence to reject the claim. If the alternative is the claim, then we say there's either enough evidence to support the claim or not enough evidence to support the claim, depending upon whether we have rejected the null hypothesis or not. Let's try this out. A consumer education organization claims that there is a difference in the mean credit card debt of males and females in the U.S. The results of a random survey of 200 individuals from each group are shown below. The 2 samples are independent. Do the results support the organization's claim? Use a level of significance of 0.05. So, a couple of key pieces of information here, okay? So, it is a random survey. That was one of the requirements. It has to be random, right? There has to be some sort of simple random sample or whatever. There are sample sizes of 200 from each group, male and female. The samples are independent. It tells us that they are independent. Okay. Sometimes you'll have to figure that out on your own. And we have a level of significance of 0.05. So here's the information that we have. Okay. The mean credit card debt for females is $2,290. The mean credit card debt for males, $2,370. Standard deviation for females, 750. Standard deviation for males, 800. Both of them have sample sizes of 200. Our null is that the 2 populations have the same debt, same average debt or same mean debt. Okay. The alternative is that they are not the same. That's all. Could be higher, could be lower, right? It could be that females have a higher debt than males, or it could be that males have a higher debt than females. All we know is the claim is that they are not equal. They do not have different, or that they do have different levels of debt. Okay. Level of significance 0.05. Based on this, is this a left tail, right tail, or two-tailed test? Two-tailed test, right? So I don't want you to see this just yet. Let's delete that. So since it's a two-tailed test, I know that each tail contains 0.025, right? That's our level of significance, 0.05 divided by 2. Each tail contains half of that. And then if I look this up, 0.025, I would get a critical value of negative 1.96. Now remember, you can use inverse norm, and you would use an area of 0.025, and then I forget with inverse norm, it's area and then what? Lower boundary and upper boundary? No? Yeah, so since we're talking about a z curve, we're looking for a critical value of z, it would want the mean of 0 and standard deviation of 1. Okay. And in this case, we would get negative 1.96. Since it's two-tailed test, we know that we also have the positive version of that, positive 1.96. Now, we need to calculate our standardized test statistic. If you recall, this is our equation. Right, and this is the sample mean of population 1 minus the sample mean of population 2, okay, minus our null hypothesis, which is the population, the mean from population 1 minus the mean from population 2. This, again, from our null hypothesis, we always assume that they are equal. We always assume that the null is correct until we've proven otherwise. So since they are equal, this is equal to 0. So we plug in the information we have, 2290 minus 2370 for our sample means, minus 0, divided by, now since our sample sizes are above 30, it's okay to go ahead and use that, that sample standard deviation that we had up here, S1 and S2. Our sample sizes are greater than 30. So we can use S1 and S2 in the place of population standard deviation values. So 750 squared divided by 200 plus 800 squared divided by 200 gives us a standardized test statistic of negative 1.03. So we go ahead and plot that on our curve. Negative 1.03 is probably about right in here. So we are failing to reject because we are in the fail to reject region, the unshaded region. And we would then say at a level of significance of 5% or 0.05, there is not enough evidence to support the claim that there is a difference in the mean credit card debt of males and females. All right, example 5. Survey indicates that the mean per capita credit card charge for residents of New Hampshire and New York is $3,900 and $3,500 per year, respectively. The survey included a randomly selected sample size of 50 from each state, and standard deviations are $900 for New Hampshire, $500 for New York. 2 samples are independent. At a level of significance of 0.01, is there enough evidence to conclude that there is a difference in the mean credit card charges? So, again, important information. We have sample means of 3,900 and 3,500 for New Hampshire and New York. Sample sizes of 50 from each state. Sample standard deviations of 900 and 500. And the 2 samples are independent with a level of significance of 0.01 as part of our test. So we just need to kind of create our own table in this case, right? X bar for New Hampshire, 3,900, 3,500 for New York. S is 900 and 500, N is 50 and 50. So we could kind of call this like you would say this is X bar 1, this is X bar 2, right? This is S1 and S2. And this is N1 and N2. Okay. Again, our null is that the two are equal. There is no difference. That's what we're assuming to be correct. The alternative is that there is a difference. But it says, is there enough evidence to conclude that there is a difference in the mean credit card charge? So we're making a claim that there is a difference. Level of significance, 0.01. We already talked about that. So since the sample sizes are greater than or equal to 30, we can assume that the sampling distribution would be normal. Since that's the case, we would set up a sampling distribution over here, bell curve, right? Two-tailed test, and each tail has 0.05. Remember, that's alpha divided by 2. So 0.05 in each tail. And again, you can either use your tables in the back of your book or inverse norm. And in this case, you would say 0.005, 0, and 1. And that would give you the critical values of plus or minus 2.575. Dang it. Let's just get rid of this. And then we need to calculate our standardized test statistic. Right? And again, remember, your test statistic is sample mean from population 1 minus the sample mean from population 2 minus our null hypothesis, mu1 minus mu2, and we assume that that is 0 because we always assume that the null is correct while we're doing the test. And if they are equal, they are 0. And then we divide by the square root of the variance from population 1 over n1 plus the variance for population 2 over n2. That's the square root of 900 squared over 50 plus 500 squared over 50. And we get a standardized test statistic of 2.747. So if I come up here to my sampling distribution and I draw in, it's kind of hard to see, but it would be right in here, 2.747, right? I am in the shaded rejection region. So we're going to reject the null hypothesis. And since we're going to reject the null hypothesis, we would say at a level of significance of 1%, there's enough evidence to support the claim that there is a difference in the mean credit card charge per capita between New Hampshire and New Jersey.